The Physics of Interstellar Travel, Chapter 5, Thermal Rockets. Most rockets are propelled by burning a fuel to produce a gas jet. This chapter examines how a convergent-divergent nozzle is used to accelerate the gas to a large velocity. This maximizes the conversion of its thermal energy, random motions, into kinetic energy, linear motion. We also take a look at commonly used liquid and solid fuels. A thermal rocket heats a gas to a high temperature and pressure in a combustion chamber that has a hole at one end. Provided the pressure of the gas in the combustion chamber is higher than the ambient pressure, the gas escapes through the hole. The gas has momentum, so by conservation of momentum, the rocket acquires equal and opposite momentum. It is accelerated. The microscopic mechanism for this momentum transfer is the collisions of the gas particles with the walls of the combustion chamber. The energy contained within a gas can be split into three parts. The thermal energy, corresponding to its temperature, the gas's potential to do work, which is related to its entropy, and the kinetic energy of its bulk motion. We can make some simplifying but reasonable assumptions, namely that the gas behaves adiabatically and irreversibly. We then find that as the gas moves from the combustion chamber towards the hole, due to the pressure difference, its temperature and pressure decrease. By conservation of energy, this results in an increase in the kinetic energy of the gas. The velocity, symbol small u, of the gas at a point where the temperature has dropped to T is given by this equation. Here, Tc is the temperature that the gas had in the combustion chamber, and Cp is the specific heat capacity of the gas at constant pressure. So as the gas moves towards the exit, it cools, converting its heat energy into gas kinetic energy, which is directed thrust. In other words, the random motions of the gas are converted into bulk directed motion of the gas as a whole. Now, the setup we see in this figure, a simple hole in a combustion chamber, would work fine as a rocket, but it's not very efficient in the sense that it doesn't extract that much internal energy from the gas. A deeper analysis shows that if we shape the nozzle to be initially converging and then diverging, we can convert more internal energy into kinetic energy and so attain a larger gas exit velocity. I explain in the chapter how and why this occurs. It turns out that the crucial factor in achieving this is to arrange that the gas velocity reaches the local sound speed at the narrowest part of the nozzle, called the throat. If it does reach the sound speed, then the gas continues to expand and cool in the diverging part of the nozzle, and the gas gets even faster. If the gas does not reach the speed of sound by the time it gets to the throat, then its pressure and temperature actually increase as it moves along the diverging part of the nozzle, and the gas will slow down again, which is not what we want. How do we know if the gas flowing from the combustion chamber reaches the sound speed at the throat? It turns out that this occurs only if A, the pressure ratio between the combustion chamber and the ambient environment where the gas exhausts to is large enough, and B, if the throat is narrow enough. This property of a nozzle to maximize the extraction of thermal energy from a hot gas is the main reason that rockets have nozzles, and almost all rockets do indeed have them. In the preceding explanation, we started with a hot gas in the combustion chamber. How this gas is heated is not relevant to how the nozzle works, but up to now almost all rockets have used chemical reactions to heat a gas propellant. Typically, a chemical fuel is mixed with an oxidizer and combusted, releasing heat. A common fuel is hydrogen, which when combusted with oxygen produces water vapor at a high temperature. This water vapor, along with any unburnt propellant, is then the gas that is ejected out of the back of the rocket and which provides the thrust. Oxygen and hydrogen are gases at room temperature, which would require very large tanks to store them, which would add a lot of mass to the rocket. These gases are therefore cooled, compressed, and stored as liquids in separate tanks in the rocket. They're then mixed in the combustion chamber and burned when needed. Under the right conditions, this can heat the resulting propellant to around 3,250 Kelvin and so achieve an exhaust velocity of about 4.55 kilometers per second. This is pretty much the most that can be achieved with a practical chemical propellant. Other liquid fuels are available instead of hydrogen, such as RP1, a form of kerosene. This produces heavier exhaust products and so gives lower exhaust velocities in a range of 2.6 to 3.4 kilometers per second. But these heavier propellants are useful for producing large thrusts. As RP1 is liquid at room temperature, it's easier and cheaper to handle than liquid hydrogen. An alternative to liquid fuels is solid fuels. Here, the fuel and oxidizer are mixed together, packed into a tube, and then ignited when needed. One has to be careful about the geometry to get the burning of the fuel right, but solid fuels and solid fuel rockets are much simpler than liquid ones. We don't need pumps and pressure regulation, nor separate cooled tanks, and the fuel is stable and can be stored in the rocket for long periods. We can't stop or throttle the burning, however. An example solid fuel goes by the name of ammonium perchlorate composite propellant, APCP, which can deliver an exhaust velocity of around 2.7 kilometers per second. Although it has less energy per unit mass than liquid hydrogen or RP1, it has more energy per unit volume, so its rockets can be relatively compact. Solid rocket fuels are often used in strap-on boosters, as are familiar with the Ariane rockets or the old NASA space shuttle. Here we see the solid rocket boosters being ejected from the space shuttle Discovery. That was just a brief summary of thermal rockets, nozzles, and liquid and solid fuels. The book chapter discusses fuels in a bit more detail and dives more deeply into the thermodynamics of how a rocket engine and a nozzle works.